Chapter 35, The Nature of Light and the Laws of Geometric Optics. We're now going to begin the second part of Physics 1C, which is called Optics. Basically, that is the study of the properties of visible light. In the previous chapter, we studied one of the most important discoveries of science in the 19th century, and that is the electromagnetic wave. According to Maxwell, the electromagnetic wave is a solution to the Maxwell's equations, and the speed of that wave in vacuum turns out to be 3 times 10 to the 8 meters per second, and that matches the speed of light in vacuum. So, it becomes clear that light really is a form of electromagnetic wave. This seems to have answered the age-old question of what is light? What exactly is light? People have pondered this question for, as you know, since the beginning of humans. There were two somewhat opposing ideas, one given by Newton and the other given by another physicist by the name of Huygens. Newton thought light was composed of tiny particles, and Huygens thought light was a wave. Okay, Newton's idea of thinking of light as a bunch of small tiny particles is not without merit. As a matter of fact, if you think of light as a whole bunch of small ping pong balls, microscopic ping pong balls, okay, and then as light strikes a flat surface, you know, those tiny little ping pong balls striking the flat surface, making an elastic collision with the surface, then it's going to come out in that direction, right? And if you draw a line normal to the surface, these two angles will be the same according to the conservation of linear momentum. So, based on this, you can predict that the light comes in at a certain angle will come off at the same angle, like this. And that actually agrees with experiment, okay, with the observation of a light beam coming in like this, coming out like that. These two angles are indeed the same. On the other hand, Huygens had a different idea. He thought light was a wave, even though he didn't really know what kind of wave that was. Remember, Newton and Huygens, those were physicists who lived before Maxwell's age. Okay, and then Newton, of course, being Newton, he had a lot of support and followers. Huygens didn't have as many, but still, the debate raged on. And one of the interesting things about that debate was that there was a French mathematician by the name of Poisson. Okay, Poisson believed in Newton's idea that light was a particle. He didn't want to think of light as a wave. He didn't want to think of light as a wave. So he said, well, if light was a wave, I want to show you something ridiculous. What is ridiculous? He said, well, if light was a wave, then suppose I have a perfect circular object. You know, you can think of a penny, for example, okay, with smooth circular border. And then light is a wave, right? So light comes in like this in the form of a wave. And I have a screen in the back. Now, light is going to drop a shadow off the penny on the screen. But he says, what's going to happen at the center of that shadow? Well, look, light coming from different parts of the wave. When they arrive at that point here, they will arrive with the exact same path lengths. And therefore, he concludes there should be what's called constructed interference, okay, at that point. So that point should be a bright spot. In other words, in the middle of the shadow of this penny, you would actually discover a bright spot. This is called a Poisson dot, okay. Seem to make no sense because nobody has seen a Poisson dot, of course, right? How would you get a bright spot in the middle of a dark shadow? Well, he used this idea to disprove Huygens' notion that light was a wave. But guess what? The Poisson dot was actually discovered, was actually observed. All you have to do really is carefully position this perfect circular shape so that it's perpendicular to the wave coming in. And that was not easy to do, but it could be done, and people have actually later observed that white dot. In fact, in our 1C lab, we're actually going to do a demonstration to show you the Poisson dot. It's actually real. It is there. Okay, so that seems to say that Huygens was right after all, because how would you understand the presence of this white dot from a particle's point of view? And that even though the debate continued for quite some time, when Maxwell discovered the electromagnetic wave and calculate the speed of that wave to turn out to be matched to be a perfect match of the speed of visible light that people already measured, it seemed clear that Huygens has won this battle. Okay, and Newton turned out to be wrong, even though he was the great Newton. So towards the end of the 19th century, we're talking about a little over 100 years ago, it seemed clear that we had a good understanding of this age-old question, which is, what is light? And the answer seems to be that it's a wave. Huygens was right. In particular, it was an electromagnetic wave traveling at a speed of 300,000 kilometers per second, which matches the speed of visible light that people have measured. Okay, now the question is this the end of the story? A lot of people thought it was. Okay, we're talking about the end of the 19th century. That was about the same time modern physics was born. Okay, modern physics has two major branches. One is Einstein's theory of relativity. That has to do with high-speed phenomena, including light. Another is the so-called quantum mechanics, which deals with microscopic phenomena, things as the behavior of molecules, atoms, electrons, and so forth. It turns out that when you look at modern physics, the border between waves and particles become kind of blurry. Okay, especially for light. It turns out that Newton wasn't wrong after all, and neither was Huygens. It turns out that light is a strange animal that can behave sometimes like particles and sometimes like waves. Okay, and for example, when the wavelengths of light wave is relatively long, such as red light, for example, you don't really usually observe the particle nature of light. On the other hand, as the wavelengths decreases or the frequency increases, the particle nature gradually starts to show up. For example, X-rays, gamma rays. These can be considered as high energy photons. Photons are particles of light, and they can behave very much like a bunch of particles. So it turned out Newton wasn't completely wrong after all, and Huygens was not completely right. Light is a complicated entity which can exhibit both particle and wave nature. And in modern physics, we have a term for that. We call it wave-particle duality. This is the central idea in quantum mechanics. Okay, one of the most important principles of quantum mechanics. But we're not going to discuss that in more detail. We will do that in 1D, not in 1C. Now, in 1C, we're going to pretty much focus on the wave nature of light, because we're talking about visible light. And in most cases, because visible light doesn't have a really, really high frequency, the photons or particles of visible light are not very energetic. So therefore, we're not going to deal with the individual photons or particles that compose of light. Rather, we're going to deal with, more generally, light as a wave. Okay, now, let's review a little bit about how the speed of light could be measured. Okay. There are different ways to measure the speed of light. One of the most successful methods of measuring the speed of light is the so-called Fittel's method. And what he did was basically, the idea was just distance over time. Okay, distance over time. The distance is not very long, so light, because it travels so fast, will cover that short distance in a very, very short period of time. So the key point is, how do you measure such a short period of time? Okay, he used the flywheel method. So imagine you have a wheel with teeth on its perimeter, and there are openings in between teeth. Now suppose this wheel spins at a very, very high rate. Okay, and there is a beam of light which happens to pass through an opening between two teeth at one moment and reflects off of a mirror and bounces back. Imagine if this flywheel turns, okay, if it doesn't turn very quickly, it does not turn very quickly. So by the time this beam passes through the crack and bounces back, by the time it bounces back, this opening is now replaced by the next tooth, which blocks the light path. Okay, so you cannot see the light coming back anymore, right? You cannot see the light coming back, so there will be a discontinuity of the light bouncing back until the next opening comes up. So then the light reflecting off of this flywheel, off of this mirror going through the flywheel will not be continuous anymore. Rather, it becomes a pulse. On the other hand, suppose you gradually increase the spin speed until it's spins so fast that by the time the light bounces off, the next opening comes in to replace the previous one. Alright? So, you see, light can once again pass through the opening without any interruption. So you will once again get a continuous reflection, not a pulse light. Right? Now, the time it takes for one opening to come over here and replace the other one is very, very short because, again, the spin rate is very high. By measuring the spin rate, which the time it takes to cover one complete turn, and by knowing how many set of teeth are there, you can figure out the time it takes to go from here to there, right? And that is the time it takes at the same time for light to go from here back to there. So you got distance, which is double that, and you got time. From that you can figure out the speed of light. So that was the first successful method of measuring the speed of light to the right order of magnitude. In fact, Pitzel got about 3.1 times 10 to the 8 meters per second, which is actually pretty close to modern values. The modern value to 2 sig figures is 3.0. So he got a reasonably accurate measurement with this rather primitive method. But the idea was very clever. Now, we're going to simply use 3.0 times 10 to the 8 meters per second to 2 sig figures for the speed of light in vacuum from now on. Okay, it suffices to say that the speed of light is very fast, even though it's not infinite. Alright, when it comes to optics, which is a study of visible light, we have to look at these two cases. Okay, treating light as a wave, we know it's called a wavelength, right? For any wave, doesn't have to be light, any wave, suppose water wave, for example. What we're going to do is we're going to consider a wave passing through an obstacle or an opening. Okay, so here in this case, we block the wave except for this tiny opening right here. In this case, the opening or the obstacle has a size which is a lot less than the wavelength. Okay, so the wavelength, could be a few meters, for example, and the opening could be a millimeter, for example. So think about water wave. As water goes, crashes onto this blockade with a tiny opening, so a few centimeters, a few millimeters. What's going to happen after water wave emerges from this opening? You know from common sense, it's going to spread in every direction, right? It's going to spread in. So this thing, you think of this as like a point source of water. So the disturbance will continue to go on, but in all kinds of directions. That is one possibility. When lambda, the wavelength, is far greater. Okay, is far greater, or in fact, it can be also comparable. It doesn't have to be all far greater. It can be also comparable. It can be as small as the wavelength can be as small as something comparable with the opening size. Okay, so you see, you cannot think of the water wave as traveling only in one straight line. It actually can diverge into different directions. On the other hand, look at another case when the wavelength is far less than the opening size. Okay, far less than opening size. Then what happens is something like this. If the opening size here, from here to there, is A, which is a lot less, which is a lot greater than the wavelength, and then light or whatever wave passing through would simply go right forward. Okay, this is the case with, for example, flashlight. Okay, for flashlight, basically the opening size is a few centimeters, right? A few centimeters. That's the diameter of the flashlight, and this is a lot greater than the wavelength of visible light, which is about half a micron. Okay, about 1/2 of a millionth of a meter. All right, We all know that as light passes through passes out from a flashlight, it pretty much travels in straight lines. It doesn't go sideways. Okay, it doesn't go sideways, unlike this case. So you see, these are two cases that we have to distinguish. In the first case, we have to consider waves traveling in different directions. In the second case, wave passing through its opening simply keeps on traveling in straight lines. It doesn't divert sideways. Okay, and since in the case of visible light, the wavelength, once again, is very short. It is about half a micron for most opening or obstacle sizes in the macroscopic world. Okay, we're talking about millimeter, centimeter, or even meters. So in most cases, as a matter of fact, we have to consider only this. When the opening size, such as the diameter of a flashlight, is much greater than the wavelength. So we only have to consider this case, in which you can think of light as traveling in straight lines. Okay, and I can figure out the direction of the straight line by drawing lines like that. Those are lines that are perpendicular to the wavefront. Okay, so these are called light rays. They indicate the direction of propagation of light. Then we don't have to consider light rays traveling in all kinds of directions, unless we really shrink the size of the obstacle or the opening so that it matches that of visible light wavelengths, or even smaller. In other words, we're looking at microns or less. Then we have to study the divergence of light in all directions. So in the first case, the wave nature is not very prominent in the first case. Okay, because regardless of the wavelengths, you can think of light as traveling in straight lines outward. Doesn't go sideways. I don't care what the wavelength is. Here in this case, the wavelength really matters. Okay, the wavelength will determine what's going to happen after light travels, and what if I have another beam of light, how did it interfere with each other. So in the first case, when lambda is a lot less than a is the size of the opening, which is very common for visible light, we do not have to consider the wave nature of light. In the second case, in this case, we really have to consider the wave nature of light. The wavelength becomes an important issue. Okay, in this case, when we do not have to worry about the wave nature of light, we can think of light, as simply traveling in straight lines called light rays. This is a case where we can simply use the propagation of light rays to predict how the light is going to behave. And we call this branch of optics the so-called geometric optics. Okay, in geometric optics, we are only concerned about light rays. We do not worry about light being a wave. We do not have to consider the wavelengths of light. Okay, in that case, the wave nature of light is important. The wavelength is important, and we have to consider the wave nature. And therefore, it is a different branch of optics. We call it physical optics. Okay, so again, we're going to separate our study of optics into two branches. Here is the wavelengths of order of magnitude of visible light, and first case, lambda much less than a. Okay, you consider light rays only. It's geometric optics, which we'll study in this chapter along with the next chapter. Okay, the differences in this chapter, we're going to outline the general principles of how these light rays can propagate. What happens when a light ray hits a border between two media? What's going to happen? And that's what we're going to study in this chapter. Okay, and then once we have these general principles, general laws in mind, we're going to study how we can take advantage of these laws to form an image using either a lens or a mirror. That is in chapter 36. We study image formation in geometric optics. But in either chapter, we will not deal with the visible light wavelengths. It's not irrelevant. It's not relevant to our study. Okay, now the second case, if lambda is comparable with a or even smaller than a, then the wave nature must be taken into consideration. We call it physical optics, and that is reserved for the last two chapters of 1C, chapters 37 and 38. And just like any wave, when you talk about the wave nature, you have common features of any wave, such as interference and diffraction, right, under the right circumstances. And in particular, for visible light, it is a transverse wave, as you know. Electromagnetic waves are transverse wave, and transverse waves will also have its own unique property. In addition to interference and diffraction, there is also something called polarization, which is also a topic in chapter 38. Okay, so this is how we're going to divide our next 4 chapters. Okay, 2 chapters on geometric optics and 2 chapters on physical optics.